Hello everyone and welcome to this webinar on electrical machines. Today we would be discussing about the principles of electrical machinery and our focus will be on induction machines. To start with, the basic topics that will be covered are the fluxes and MMFs in induction machine, the rotor action, how the magnetic fields are created, how do we go to the equivalent electrical circuits, and so on. To start with, we will be looking at the basic feature of the induction machine. So the explanation of the induction machine in today's webinar will be done with the help of a motor which has 12 slots on the stator and 16 slots on the rotor, and the machine that is considered here is a cage rotor induction motor. The detailed configuration of the machine is shown here in figure 6.1, and one can see that there are slots on the stator and slots on the rotor. It's a very simplified diagram of the induction machine. The slots are not shown in details over here, this is just for the illustration purpose. And here in this second figure we show the winding layout. So a single layer winding is considered to keep the analysis and the explanation of the machine simpler. However, in real machines we use double layer windings. Here we can see that since it's a single layer winding, there are two coils per phase, and the color scheme that we have used is RGB, where R is for red and it represents phase A, G is for green which represents phase B, and B is for blue which represents phase C. So here we can see the various coils of each phase. Now, before we go into the understanding of the electrical machines in detail, it's important to understand how the machine looks like, what are the various components, and this is shown in this 3D video. So here we will be looking at the de-assembly of an electrical induction motor, a cage rotor motor. So the various components of the machines would be de-assembled step by step to give a clear illustration of what are the constituent subsystems of an complete induction machine. Now we can see here the machine was housed inside a housing. There was a cooling fan, it's an air-cooled motor, and then inside the housing is the actual electromechanical parts of the machine. So it constitutes of bearings, and then there are two bearings and coils on the stator, and also a layer of insulation which separates the coils from the ferromagnetic material. So this provides the electrical insulation. And then we have the stator, which is made up of various laminations, and then the end rings, and after the end rings are done, the rotor bars come out. So the purpose of the end ring is to short circuit these rotor bars at both the ends, and this is the ferromagnetic part of the rotor. And then also the animation further goes on to explain how actually the windings are made. So here we can see how copper strands are eventually converted into coils. So the coils are prefabricated, and then these prefabricated coils are then inserted into stator slots. Before inserting them into the stator slots, a layer of insulation is placed, which we can see here in this video. A green color layer of insulation is placed inside, and once all the insulation layers are placed, the coils are put in position, and the position of the coil depends on the coil pitch and the winding scheme of the machine. So with this, actually one gets a clearer perspective of how the machine is manufactured. And here on top in this animation we see a plastic strip is placed so that the coil remains in place and does not move when the machine is in construction or in operation, sorry. And eventually the machine is dipped into a resin to insulate it completely. So this was in detail the explanation of the construction of the machine. Now, after having understood the construction of the machine, it's actually quite interesting to play with various components of the machine, and this is enabled by this interactive 3D animation. Here on the top left corner we see the terminal box, and then we place that here in position, and one can see in detail how the terminal box looks like and what is its function. And then we come to the next part, which is the stand, and these stands are placed over here, and one can see in detail about the function of the stand and what is it made up of. And then the front cover of the machine is placed, and here one can see a complete 3D view of how the front cover in principle looks like. And this is the cooling fan. The purpose of the cooling fan is to provide forced cooling to air-cooled machines. So the machine which we are showing here is an air-cooled machine. There are other types of coolings which are available, such as oil cooling, water cooling, and so on. And these are the bearings, and the rotor is supported on these bearings, and the bearings are fixed to the housing of the machine. Then we go into the coil, and here is the stator coil, and this is how the stator coil is going to look like if we visualize it from a 3D perspective. And next comes the insulation layer, and we place it in the proper box, and by double clicking it we see how the insulation looks like. Next comes the stator. The stator is actually made up of various laminations, and these laminations are stacked together to form the stator. Now the purpose of having laminations is to reduce eddy current losses inside the machine. So if we don't use laminations, then the eddy currents are going to be quite huge, and the end rings are used to short circuit the bars of the rotor. As we discussed earlier, the machine that we are discussing today is a cage rotor induction motor, so all the bars of the rotor are short circuited, and this short circuiting is done using the end rings which are present at both the ends. And then in this fashion one can actually keep on doing or keep on deassembling each and every component of the machine. So this in principle makes the construction details of the machine more interactive and helps the user to get a feel of the actual system. Now after having done that, we go back to our topic on induction machine, and the first animation that comes up here actually explains how a rotating magnetic field is created by the three-phase windings on the stator. Now windings is one topic which is very important and essential to understand, and this can be done easily with the help of an interactive animation which is known as winding over here. So here, for example, we will choose some number of slots. So we choose 9 slots on the stator, and we want to design a winding for a 2-pole machine, and the winding which is valid for a 9-slot machine and is able to produce 2 poles is this, and we will have to just fill up the table completely, and after filling up the table we will see how the magnetic field actually looks like due to this winding. It really is quite instructive and helps the reader to understand whether the winding is correct or not. And then we click on the winding and we see all the phases. So here, corresponding to the winding scheme that was entered here, we can see the winding layout here. The dots and the crosses indicate in and out. So here we can see the first coil of phase A. It went inside slot 1 and came out at slot 5. So it went inside in slot 1 in and came out at slot 5 out. Same way, the second coil of phase A went in slot 1 and came out in slot number 6. And same way, the third coil of phase A went in slot number 2 and came out in slot number 6. Similarly, we can see how the winding is laid out for phase B and for phase C. So the green color indicates phase B and the blue color indicates phase C. And if to this balanced three-phase winding, balanced three-phase double layer winding to be more precise, if we feed a three-phase balanced current to these windings, then we would be seeing magnetic field which rotates with time. So the balanced three-phase winding, when excited by a balanced three-phase current, is going to produce a rotating magnetic field. Now, to get a better perspective of this, we can also go into the analysis of the machine further. So this actually illustrates that how a rotating magnetic field is created, and this is shown over here, a rotating magnetic field. Now, due to this rotating magnetic field, all the further phenomena inside the machine take place, but it's very important to understand the concept of rotating magnetic field. So in the previous animation, here we saw that as time progresses, the magnetic field changes its position in space. Now, if we assume that at a given time instant the magnetic field remains frozen, it does not move, then how would it look like? And this can be seen here in the animation. If we take a Hall sensor and move along the periphery of the air gap, so the starting point is here just below the North Pole, and with the Hall sensor, if we rotate or if we move in anti-clockwise direction, then the Hall sensor is going to measure a magnetic field which is shown here in this curve. So this is a very sinusoidal distribution of the magnetic field. It's just for the illustration purpose. In actual electrical machines, the magnetic field is seldom purely sinusoidal. There are multiple harmonics present due to the slotting effects and so on, but these are not considered here because the purpose of this webinar is to describe how exactly an induction machine works. So at a given time instant, the time instant t1, this was the orientation of the magnetic field. Now if we change the currents fed to the windings are three-phase currents. So if we take currents at some other time instant t2, the magnetic field would have rotated by 90 degrees in anti-clockwise direction. And again, if we take the Hall sensor, the starting position of the Hall sensor is still here where the mouse is placed, and if we rotate in the anti-clockwise direction, the field that the Hall sensor is going to measure is shown here in the curve, the sinusoidal curve. So we can see that the sinusoidal curve has now shifted by 90 degrees. The peak of the curve, which appeared initially at 0 degree, now appears at 90 degrees. Similarly, if we go to the next time instant t3, we can see that the magnetic field produced by the stator winding has moved further by 90 degrees. And again, if we take a Hall sensor and start from the same initial position which is shown by the mouse over here, and if we move in anti-clockwise direction with our Hall sensor, then we can see that the magnetic field is shifted by further 90 degrees. And in this fashion, we can carry on and see how the magnetic field looks like at time instant t4, and then how it looks like time instant t5. So in this fashion, one can actually understand that how the magnetic field is created by three-phase windings when excited by three-phase currents. It's all a balanced system, and due to this rotating magnetic field, the bars in the rotor would be linking the bars in the rotor would see a changing magnetic field. Now, if the bars in the rotor see a changing magnetic field, then there would be an induced EMF given by Faraday's law of magnetism. So which says that EMF induced is minus d lambda by dt, where lambda is the flux linkage. And here we can see how the flux is linked by each of the bars. So to understand, this figure shows the flux linked by different bars at time instant t1, and one can actually go back to the animation which was for time instant t1, which is this over here. So if we see over here, these are the bar 4 and 5. So these bars actually enclose maximum number of flux lines, whereas bar 1 encloses the least number of flux lines. Similarly, bar number 13 and bar number 12 link maximum enclose maximum number of flux lines, and bars 15 and 9 enclose minimum number of flux lines. And this is what is illustrated here in the figure, which demonstrates the flux linked by the bars. So this is the bar number 1, which link the minimum flux lines or enclosed minimum flux lines. Bar 4 and 5 enclosed maximum number of flux lines. Similarly, 12 and 13 enclosed maximum number of flux lines, and 9 and 16 enclosed minimum number of flux lines. So the flux lines enclosed by the rotor bars are also sinusoidal, because we have assumed the field produced by the stator winding is sinusoidal. So this is the situation of the flux linked by the bars at time instant t2, and here is the situation of the flux linked by the bars at time instant t2. Since our magnetic field has rotated by 90 degree in anti-clockwise direction at time t2, the flux linked by the bars also changes, and similarly at time t3 and t4 the fluxes change. Now we can see here that as the magnetic field of the stator rotates in space in anti-clockwise direction, the flux linked by the rotor bars also change, and this changing flux of the rotor bar actually induces an EMF given by the Faraday's law, and the EMF induced in each and every bar at each instance of time t1 to t4 is shown here in figure 6.8a, b, and then in figure C and D. And here we see that this is the animation about how the flux is enclosed by the rotor bars. Since the rotor is stationary, we can see here the rotor does not change its position. It's only the stator magnetic field which rotates. Due to that, the flux linked by different bars, the bars are labeled as SL1, SL2, SL3 here in the graph. It changes continuously, and due to this changing bar, the EMF is induced in the in each and every bar. Now, due to the induced EMF, the currents would start to flow in the bars. So we can see the sequence here. The rotating magnetic field of the stator results in flux linkage, which changes with time in the rotor bars. Now this changing flux linkage in turn induces EMF in the rotor bars, and due to this EMF we have currents in each and every bar, and the magnitude of the current would change because we have seen that each bar links a different magnitude of flux at different instants of time. As a result of that, it produces different magnitudes of EMF at different instants of time, and hence the current in each bar would be different at different instants of time. And this is what is being explained here in the theory part. And we can see here in the animation that how the current flowing in each and every bar changes as the stator's magnetic field changes its position. Here one can see that the bigger dots and crosses indicate larger magnitude of the current, and the smaller dots and crosses indicate the smaller magnitudes of the current. So now we are playing the animation rather slow, so one can see here, if you focus on bar number 1, so initially the current gets larger, then it decreases in magnitude, then it changes its direction, its magnitude increases, and so on. So this is how one can actually visualize how the currents are induced or currents are made to flow in the bars of the machine. Here we have to remember, since it's a cage rotor, the bars are actually short-circuited at both the ends, and hence a current has a path to flow. And this also can be understood in detail by using the Fleming's right-hand rule. So in this box 6.1, the Fleming's right-hand rule is explained that if we know the direction of the magnetic field and the currents, then we can actually determine how exactly is the machine going to work and what will be the direction of the currents inside the machine. So we will go back to the point where we had left and we will see further the analysis of the machine. Now we come to the next part, which is the magnetic field created by the rotor bars. So the sequence of events is as follows. The rotating magnetic field of the stator resulted in time-varying flux linked by the rotor bars. Due to this time-varying flux in the rotor bars, EMF was induced in each and every bar. Now since the bars are short-circuited at both the ends by the end rings, due to the induced EMF, the current flows through in each and every bar, and now due to the current in the bar, a magnetic field is created. So we can see at time instant t1 the direction of the currents are shown over here, and from this one can determine by the right hand rule the direction of the magnetic field created by the stator by the rotor currents. So N2 and S2 represents the direction of the magnetic field created by the rotor bars, whereas N1 and S1 is the direction of the magnetic field created by the current flowing in the balanced three-phase winding of the stator. So we can see that we have two magnetic fields, N1 and S1 due to the stator and N2 and S2 due to the currents in the rotor, and these fields, magnetic fields, are displaced in space by 90 degrees with respect to each other. At time instant t2, when the stator magnetic field rotates by 90 degrees, the rotor magnetic field also rotates by 90 degrees. And this happens for time instant t3 and t4 as well. So we can see that at each and every time instant the angle between the stator and the rotor magnetic field remains constant. It remains at 90 degrees, which is an important point. For any kind of a machine, be it an induction machine or a synchronous machine or a DC machine, the important thing is that the angle between the stator and the rotor magnetic field should remain constant at each and every time instant. And to produce maximum torque, the angle between the two fields should be equal to 90 degrees, and this is what is exactly happening here in case of a cage induction motor. And once we have the two magnetic fields, we can also determine the direction of the torque, and this torque acts on the periphery of the rotor. So in figure 6.11a, we can see the direction of the torque which is acting on the periphery of the rotor, and this torque is actually determined by Fleming's left hand rule, about which we had seen in box 6.1. Similarly, at time instant t2, when the magnetic fields have rotated by 90 degrees, we can again see the direction of the torque acting on the rotor periphery. So we can see that at each instant of time the direction of the torque acting on the rotor periphery is tangential, and hence the rotor starts to rotate in anti-clockwise direction. So this explains that how the interaction of the two magnetic field eventually results in the production of the torque in the cage rotor induction motor. And this animation here gives us a complete overview of how the how various phenomena take place inside the machine. So on the left we can see that the stator's magnetic field is rotating, which results in currents in the rotor bar. And here this second animation in the first row shows the flux linked by the rotor bars, and due to this flux linkage we have induced EMF, which is shown in the animation 1 in the second row, and due to this induced EMF in each and every bar of the rotor, current flows through the bars, and this is shown in animation 2 in row 2. So one can actually see those animations more precisely in slow motion, and we can see that the flux linkage and the induced EMF have a phase shift of 90 degree, and the current and the EMF are in phase because here we have neglected the inductance of the rotor bars. So we have assumed the rotor bars to be purely resistive in nature, and as a result of that the induced EMF and the bar currents would be in phase, and this is the phasor representation of the in rotor. So this is the flux which is linked by the bars. This is the induced EMF in the rotor bars, and this is the current in the rotor bars. And due to these currents, we have an MMF produced by the rotor bars. So we can see that the flux linked by the bars and the induced EMF are displaced by 90 degrees, whereas the induced EMF, the current and the MMFs are in phase. The induced EMF and the current are in phase because we have considered the rotor to be purely resistive in nature and we have neglected its inductive component. Similarly, to extend the analysis further, here we discuss about what happens if we do not neglect the inductance of the rotor or we take that into account. Now, due to the inductance, the current would start to lag, and this is what is being demonstrated here over the next sequence or the next phasor diagram that we have. So we can see that the flux and the induced EMF would be in phase, but due to the inductance of the rotor, the current would lag the induced EMF by a certain angle theta 2, and this angle is also known as the rotor's power factor angle. And then one can actually understand the principle of the, or one can understand the impact of the rotor inductance on the behavior of the machine. So here in this animation one can see that the flux linkage and the induced EMF are displaced by 90 degree, whereas the induced EMF and the current in the rotor bars are not in phase. Rather, the currents lag the induced EMF, and this happens due to the presence of inductance in the rotor bars. Similarly, after having discussed a two-pole machine, one can understand or analyze the operation of a four-pole machine in the similar fashion. And here, to illustrate the operation of a four-pole machine, we have again considered a machine which has 12 slots on the stator and 16 slots on the rotor, but the winding is now done in a different way, and now this winding is capable of producing 4 poles, and it's a double laid winding, and the 4 poles of a machine look in this fashion here as shown in this animation. So this creates a rotating 4 poles. So the winding which is shown here in this figure, if it's excited by a 3-phase balanced current, then the magnetic field is going to look as we can see here in this animation. And similarly, one can carry on the analysis further and see that if the magnetic field is frozen in time and if we move with the Hall sensor, then in 360-degree rotation the Hall sensor is actually going to measure 2 cycles of the magnetic field, because since we have a 4-pole machine, so there are 2 north poles and 2 south poles, and this is how the machine is actually going to look like. Similarly, as the magnetic field of the stator rotates, we can see that how the orientation of the field looks like at different instants of time. Here the field has again rotated by certain angle, and then here the field has rotated further at time instant t4, and due to the rotation of the stator's magnetic field, the flux linked by the rotor bars would also be changing, and these are shown here in figure 26.21a to 6.21d. And this figure shows the EMF induced in the rotor bars, and due to the induced EMF in the rotor bars, we would be having currents in the rotor bars, which are shown here in the figures 6.23a to 23d for different time instants. And due to the currents in the rotor bar, we would be having a magnetic field created by the rotor bars. So we can see here the rotor had same number of bars, 16 bars. The 2-pole machine also had 16 bars, and the 4-pole machine also has 16 bars. But this is the inherent nature of the cage rotor induction motor, that it is able to adapt itself to any number of poles created by the stator winding, and this is precisely what we see here in this series of figures. And the animation over here shows that how actually the machine is going to operate. So with this, actually, we can understand the principles of cage rotor induction motor, and then it carries on further to develop the phasor diagram. Now after having done the cage rotor induction motor, the discussion moves on to the two-pole wound rotor induction motor, and in this case we have proper windings on the rotor instead of bars. So one can see here how the windings of the rotor looks like. So in case of a wound rotor motor, we have a winding on the stator and we have windings on the rotor. So there are 3 coils per phase on the rotor. So 3 coils for phase A shown by this red color, 3 coils for phase B shown by the green color, and 3 coils for the phase C shown by the blue color. And these 3 coils actually will produce 2 poles. So if we place this rotor inside a stator which is producing 4 poles, then the machine will not be able to produce torque because this winding is capable of producing only 2 poles. So now here comes the major difference between the cage rotor motor and the wound rotor motor, that the cage rotor is able to adapt to any number of poles that the stator is producing, whereas in case of a wound rotor motor, one has to wind the rotor accordingly and produce the specified number of poles. So the discussion over here goes into how the wound rotor motor is going to work upon, and this is all again the electromagnetic viewpoint of the machine, and it gives a detailed explanation of how exactly the operation of a wound rotor motor is done. So it explains both the 2-pole machine and the 4-pole wound rotor motor, and it's quite elaborate and enriched. And after it has been done, we eventually move on to the equivalent circuit, the electrical equivalent circuit. So the first half of the chapter deals with the magnetic phenomenon that take place inside the induction machine, both the cage rotor and the wound rotor machine, and the second half actually goes towards the electrical equivalent circuit. And here the classical treatment of the machine using the electrical equivalent circuit is presented, and here we can see the electrical equivalent circuit of the rotor and the electrical equivalent circuit of the stator, and then how do we eventually combine these electrical equivalent circuits. Now to understand the principles of electrical equivalent circuits in detail, one can actually go to the tools, and here it shows the basics of equivalent circuit. So this is just a simple equivalent circuit to illustrate that how the machine would behave. Here, to keep the things simple, we have neglected the magnetizing branch, and we give some value of the voltage, the stator resistance, the leakage inductance of the stator, and the leakage inductance of the rotor. These values are displayed over here as well, and then we see that how the current would look like as we change the rotor resistance. So the rotor resistance over here is a variable quantity, and we can see the influence of changing the input voltage parameter on the current. This is the stator current, and by changing the rotor stator resistance, we can see the impact on the current. So it changes its magnitude as I increase my stator resistance. Similarly, the stator leakage inductance also has an impact on the current in the stator and the rotor leakage inductance as well. Similarly, the impedance of the circuit, it would be independent if I vary the voltage, whereas it would be a function of the stator resistance, stator inductance, and the rotor inductance. So this tool actually helps the reader to see the sensitivity of the parameters on the machine's various output characteristics. So various output characteristics can be analyzed, and we can see the impact of changing some parameter on the output characteristics. So it enables the reader to correlate the theory with the practical experience. Now, having done that, the next important thing is to understand and to do the process in more detail, and this is done with the help of the virtual lab. So here we have the same equivalent circuit. It's a more detailed involved exercise. So a problem statement is given which one has to read carefully, and after having read the problem statement, a series of questions would appear which are designed to check whether the reader has understood the question properly. Now this is the first question, and for this first question I have to choose the answer based on the understanding and the theory that I have read in the ebook. Now if I choose an option D, it happens to be the wrong option, so I can either retry or I can go for hint, and by clicking the hint I get an idea that okay, this is how I should try to find the proper answer, and the answer is A. Similarly, we come to the next question, so I will be just answering them fast so that one can move on to the next level and see that what it does. So we are at the last question, and after having answered this pre-lab question, we come to the more detailed analysis part. So here I enter some values of the parameters that I would like to evaluate and see what output do I get. So I have entered the values. If the ranges of the values are given over here, and the calculation is done. So let's go and have a look at the results. So I get the resistance, the rotor resistance versus current graph for the parameters that had been entered. Now the first question is calculate the impedance of the circuit. Now to calculate the impedance of the circuit, the student has to look on the, or has to choose a proper value from the first column and from the second column. So the impedance of the circuit can be determined by this, and then the operation that would be needed is square root, and here we have the impedance of the circuit and the graph immediately appears. Then we go to the next question. So it is to calculate the RMS value, and it is division, and we see the result immediately. So it is 1 and then 4, and it is the multiplication between them, and then we go to the next question. So we can see here that it's really an involved exercise, and the student has to actually work and do the calculations and can see the results immediately. So this set of exercises actually reinforce the theory that have been studied previously in the ebook, and enables this reader to appreciate the various fundamentals that have been introduced in the text of the ebook. And now I think we are approaching to the last question, and this is what we have. So eventually we have finished the level. Now based on the calculations done in that level, we will be answering few questions. So here comes the first question, and to answer that question we will look at the appropriate graph. So to look at the appropriate graph, we would see that okay, maybe this graph is able to answer my question, so it's a correct answer. Now to answer the second question, I have to choose a proper graph which would help me to analyze, to arrive to a proper answer. So these graphs are based on the calculations which were done in the previous step. So based on that, by looking at the graphs, we try to choose the proper answers, and this way one can actually answer each and every questions. And then comes the next level. So in this next level, actually we again try to do some sensitivity analysis. So the default calculation was done for 200 volts. Now we want to do the calculations for 100 volt and 300 volt, other parameters remaining constant. And then what one can do is see the impact of voltage on the current. So we see here, as we increase the current gradually, as we increase the voltage gradually, sorry, the current increases, and then we can see the impedance of the circuit remains unchanged because voltage has no bearing on the impedance. Similarly, the RMS value of the current also changes. So after having done that, one has to answer a series of questions based on the analysis done over here and see how actually the analysis works. Now, after having done this series of after having answered this series of questions, one come to the final level, which are mostly the discussion questions. Now, the other important part which is required to understand is actually the quiz. So once the student has been subjected to the ebook, the various animations and so on, the evaluator or the instructor would like to test whether the student has answered or understood all the questions properly or not. So here one can choose the quiz for each and every question. So we were on chapter number 6, so we choose the quiz over here. I would choose 5 questions and maybe I'll give 10 minutes duration, and each question would have 4 marks for right answer and 1 negative 1 for the wrong answer. And here we enter the student's name and its roll number, and the quiz starts. So I give the answer to the first question, then I give the answer to the next question. For the fourth question, I don't know the answer. For this I give some. So I have finished my examination, and here is the results. So I didn't answer any question correct. I answered 3 questions wrong. My total marks are 0. So this is how the quiz ended. And now the evaluator can eventually go to the quiz and see how the student fared in the examination. So we go to the analysis, we go to the browse, and then we see the student's performance, the answer script of the student, and then see that how the marks of the students look like, and this will help the teacher to see whether the student fared well and what are the weak points of the student. So here in this presentation we have shown that how different uh, techniques can be used to analyze the students' performance. So we have the ebook. The ebook is enriched by the 3D animations, then there are interactive animations, then there is a virtual lab, and eventually an evaluator. This together constitutes a complete package on e-learning on electrical machines, and today's discussion was about induction machine. I hope you found this webinar to be interesting, and I thank you very much for joining this webinar, and see you in our next webinar. Thank you very much for your time and patience.